Today, we will be going through section 1.3, rates of change and behavior of graphs. Goals. Today, we set out to 1. Compute the average rate of change of a function given its equation, table, and graph for specific points. 2. Compute the average rate of change for a function for an abstract interval. 3. Analyze the graph of a function to determine the following: A. Extrema, B. Intervals of increase and decrease, C. Intervals of concavity, and D. Points of inflection. What is rate of change? Suppose we have a function k of x and we only know 2 points of the function. I'm going to show a table with 2 rows, x and k of x. In the x row, we have the points 2, 3, 4, 5, and 6. In k of x, we have y in the first. What is rate of change? Suppose we have a function k of x and we only know 2 points of the function. I've got a table with 2 rows, x and k of x. In the x row, I have 2, 3, 4, 5, and 6. In the k of x row, I have 1, and then I don't have any associated y values for 3, 4, and 5, but I have the y value of 9 associated with 6 on the x row. I have an XY grid shown, and I have the coordinate points 2, 1, and 6, 9 clearly demarcated. Could we make an educated guess about the other points on this function? Let's see how much we expect the function to change in y values per x value. Our change in y divided by change in x equals 9 minus 1 divided by 6 minus 2, which equals 8 over 4, which is equal to 2. For every unit we move over, we move 2 units up. On my table, I show an arrow going from x equals 2 to x equals 3 in the y value. So 1 goes to 3 after I add 2, and then I do that same arrow with a plus 2, taking me to 5. And then I add 2 to that 5 to make it 7. And then that 7 brings me to 9 by adding 2. On the graph, I showed coordinate points sliding up into those pairs. In particular, 2, 1, 3, 3, 4, 5, 5, 7, and 6, 9. But wait, there's another way. From the graph, we could just draw a straight line between the points 2, 1, and 6, 9. And see what the line predicts. On this line, I see a clear demarcation of the coordinates 3, 3, 4, 5, and 5, 7, which are all the coordinate pairs in between 2, 1, and 6, 9. This line is called a secant line. And as we saw from the table, its slope is the rate of change of the function over the specified interval. We have the formula m equals y2 minus y1 divided by x2 minus x1, which is equal to 9 minus 1 divided by 6 minus 2, which is equal to 8 divided by 4, which is equal to 2. Rate of change. A rate of change describes how the output quantity changes in relation to the input quantity. The units on a rate of change are output units per input units. Computing the rate of change from an equation. Example, calculate the rate of change of the function over the interval -1 to 5, both of which are in brackets. The function we have given is f of x is equal to 3 times the absolute value of x minus 4 plus 1. Procedure. Step 1. Compute the coordinate pairs of the endpoints of the specified interval. So here we have 2 coordinate pairs. We do not know the y values, so those are left blank. And our x values are -1 and 5 respectively, because that's the interval over which we are finding the rate of change. So I'm going to plug -1 in first as my x value. So I get 3 times the absolute value of -1 minus 4 plus 1. By order of operations, I compute what's in the absolute value brackets first. -1 minus 4 is -5. So now I have 3 times the absolute value of -5 plus 1. The absolute value of -5 is 5. So now I have 3 times 5 plus 1. That's equal to 16. So now my y value for my first coordinate pair is 16. Thus, I have the coordinate pair -1, 16. Now, for 5, I'm going to make that my x value to find the y value for the second coordinate pair. So now I have 3 times the absolute value of 5 minus 4 plus 1. By order of operations, 5 minus 4 is 1. So now I have 3 times the absolute value of 1 plus 1. Observe that the absolute value of 1 is 1. So now I have 3 times 1 plus 1 is equal to 4. So now I have the coordinate pair 5, 4. Now that I have these coordinate pairs, I can move to the second step of the procedure. Use the rate of change formula, m equals y2 minus y1 divided by x2 minus x1. So now I have m is equal to y2 minus y1 divided by x2 minus x1, which is 4 minus 16 divided by 5 minus -1. 4 minus 16 is -12 divided by 5 minus -1, that's 6. So I end up with -12 divided by 6, which means that m is equal to -2. That is my rate of change of the function 3 times the absolute value of x minus 4 plus 1 over the interval -1 to 5. Summary. Rate of change. What is it? The rate of change of a function f of x tells us the rate at which f of x changes with respect to x. How do I calculate it? Given two coordinates, x1, y1, and x2, y2, we calculate the rate of change m below. M equals y2 minus y1 divided by x2 minus x1. I am drawing a box around given two coordinates x1, y1, and x2, y2 as a point of emphasis. From a table, we use the endpoints given in the table to get coordinate pairs. This is what we use in our slope formula, which is why the box was drawn around the statement given two coordinates x1, y1, and x2, y2. From a graph, we determine the coordinates of the endpoints from their x and y values on the graph. And then from an equation, we plug the x values of their endpoints in to find their respective y values. So in short, no matter how we're given a function, whether it be from a table, a graph, or an equation, we are always in effect looking for two coordinate points in order to find the rate of change between those 2 points. Computing an abstract rate of change. Example, determine the rate of change of f of x over the interval 2 to 2k in brackets. F of x equals -x squared plus 9. Procedure. Step 1. Compute the coordinate pairs of the endpoints of the specified interval. Observe that our procedure hasn't changed at all, even though we're moving over an abstract rate of change, meaning that it's not from 2 to, say, 5, rather it's from 2 to something like 2k, where we have a variable endpoint. We still have our two coordinate pairs. We don't know the y values. So I've got a coordinate pair with x filled in as 2, the y is left blank, and our other coordinate pair, 2k, is filled in as the x value, but the y value is left blank. I will find the y value of the first coordinate pair by plugging 2 in for x. So I get negative and then 2 squared plus 9. Well, that's going to be -4 plus 9. That's equal to 5. So the y value for my first coordinate pair is 5. Now I'm going to plug 2k in for x. So I get negative, and then in parentheses, 2k squared plus 9. That comes out to -4k squared plus 9. So now my y value for the second coordinate pair is -4k squared plus 9. It is not a bad thing at all to have a y value in terms of a variable. Step 2 in my procedure, use the rate of change formula, m equals y2 minus y1 divided by x2 minus x1. So m is equal to y2 minus y1 divided by x2 minus x1. So I have negative 4k squared plus 9 minus 5 divided by 2k minus 2. I simplify the numerator and I have negative 4k squared plus 4 divided by 2k minus 2. Now I factor a negative 4 out of the numerator. The negative goes out front of the fraction in its entirety. So now I have negative 4 times k squared minus 1 in parentheses divided by 2 times k minus 1 in parentheses. So now step 3 in the procedure is simplify as needed. So now I have negative 4 k squared minus 1 in parentheses divided by 2 k minus 1 in parentheses. Observe that k squared minus 1 factors to k plus 1 times k minus 1. So I factor that, and so now I have negative 4 times k plus 1 times k minus 1 divided by 2 times k minus 1. I draw lines through the k minus 1 in the numerator and the denominator in order to signify cancellation. I draw lines through the 4 and the 2, numerator and denominator respectively, to show cancellation, and the 4 changes to 2. So I change that 4 that's slashed out into a 2. And so now I have negative 2 times k plus 1. Or, after I distribute the negative 2, I have negative 2k minus 2. And that is my rate of change of the function f of x over the interval 2 to 2k, where the function f of x is negative x squared plus 9. Computing an abstract rate of change. Example, determine the rate of change of g of x over the interval 6 to 6 plus h. The function g of x is 1 over x minus 3. Procedure. Step 1. Compute the coordinate pairs of the endpoints of the specified interval. Again, I have my coordinate pairs with 6 filled in as the x value, the y value left blank, and 6 plus h filled in as the other x value and the y value left blank. I will plug 6 in, so I have 1 over 6 minus 3 for my y value, which is 1 over 3. 1 over 3 is my y value for the coordinate pair with x equals 6. Now, I'm going to find the y value where the x value is 6 plus h. So now I have 1 over 6 plus h minus 3. I collect up like terms, and the 6 and the minus 3 collect. And so now I have 1 divided by 3 plus h as the associated y value for the coordinate pair with x being 6 plus h. Step 2 in my procedure. Use the rate of change formula. M equals y2 minus y1 divided by x2 minus x1. M equals y2 minus y1 divided by x2 minus x1. So I have 1 over 3 plus h minus 1 over 3 divided by 6 plus h minus 6. Observe in the denominator that the 6's cancel. Step 3 in the procedure is to simplify as needed. So now my denominator is h. In my numerator, I have 1 over 3 plus h minus 1 over 3. The trouble here is in order for me to do this subtraction, they need to have common denominators. So for the term 1 over 3 plus h, I'm going to multiply that term in particular by 3 over 3. And the term 1 over 3, I'm going to multiply that term by 3 plus h divided by 3 plus h. This will give me the common denominator of 3 times 3 plus h. And so after I do that and distribute the necessary terms, in the numerator, I have the fraction 3 minus h over 3 times 3 plus h. And in my denominator, I have just h. I draw lines through 3 and minus 3 to signify their cancellation. And now, after I re-express my fraction as a multiplication of reciprocals, I have negative h over 3 times 3 plus h times 1 over h. I draw lines through the h's in order to signify cancellation through division. And now I have that this is equal to negative 1 over 3 times 3 plus h, which is also equal to 1 or negative 1 over 9 plus 3h. Either of these answers are acceptable and correctly compute the rate of change of the function g of x equals 1 over x minus 3 over the interval 6 to 6 plus h. We will now talk about intervals of increase and decrease of a function's graph. Increasing/decreasing. A function is increasing on an interval if the function values increase as the inputs increase. More formally, a function is increasing if f of b is greater than f of a for any two input values a and b in the interval with b being greater than a. The average rate of change of an increasing function is positive. Now I show a picture of an XY grid. I allow for the point 1, 1 to be clearly demarcated as I am discussing the increasing nature of a function. As I go to the right on the x-axis, so I now send another point as a counterpart going to the right. I go up on the y-axis. So then I send that point above the line y equals 1 on this grid, and I fill in a line between them. So what I'm demonstrating is that as I go to the right on the x-axis, I am forced to go up on the y-axis if the function is increasing over this interval. A function is decreasing on an interval if the function values decrease as the inputs increase. More formally, a function is decreasing if f of b is less than f of a for any two input values a and b in the interval with b being greater than a. The average rate of change of a decreasing function is negative. I go back to my grid, my XY grid. I clearly demarcate the coordinate pair 1, 1. As I go to the right on the x-axis, so I take another companion point and I send it to the right of 1, 1. I go down on the y-axis. Now that point moves downward, a vertical line, and I fill a line in between those 2 points. This is to demonstrate that if a function is decreasing over an interval, as I move to the right on the x-axis, I am going to be moving down on the y-axis. Now I have a picture of a graph. This is a quadratic parabola pointing downward with a vertex at the coordinate point 2, 4. Here, I'm going to find my interval of increase and my interval of decrease. I'm going to start by drawing a vertical line at x equals 2 to clearly demarcate where we are increasing and where we appear to be decreasing on this graph. To the left of the line, x equals 2, I color in the quadratic parabola green as if to show that we are increasing over this space. The leftmost endpoint of where this begins to happen is when x is equal to negative infinity, as if to say all the way to the left. So I use a parenthesis and then negative infinity. And then at x equals 2, we stop increasing, and I use a parenthesis there. So my interval of increase is from negative infinity to 2, both of which are getting parentheses. Now I color in the portion of the quadratic parabola to the right of x equals 2 red, as if to signify that this function is decreasing over this space. This interval would start at x equals 2, so I show 2 with an open parenthesis to its left. And it would be decreasing all the way to the as x goes to the right, i.e. x is approaching infinity, for which I'm going to put a parenthesis around that as well. So my interval of decrease would be from 2 to infinity, both of which are in parentheses. The next function that I'm showing is a quartic function. Both arrows are pointing down, and I have turning points at the coordinate pairs 0, 5, 2, 3, and 4, 5. Okay, the function has an M-like shape to it. And again, the turning points of this graph are 0, 5, 2, 3, and 4, 5. I start by drawing vertical lines at x equals 0, x equals 2, and x equals 4. This helps me partition my graph into very clear spaces where it is either increasing or decreasing. I'm going to start by writing my intervals of increase. The space most to the left of the line x equals 0, I'm coloring that green. This function, or this space, signifies an interval of increase which starts at x equals negative infinity, as if to say all the way to the left, and it stops at x equals 0. So I use the interval negative infinity to 0 with parentheses for both endpoints. Next, I examine the space from 2 to 4 on the x-axis, so the space in between the lines x equals 2 and x equals 4. I'm going to use 2 and 4 in my interval there with parentheses because this is also where the function is increasing. For intervals of decrease from x equals 0 to x equals 2, I color that space in red as if to show that we are clearly decreasing. So I use the interval 0 to 2 with parentheses around both of those endpoints for one interval of decrease, and my other interval of decrease starts at the line x equals 4 and continues all the way to the right on the function, in particular x equals infinity, and I'm going to use parentheses around that interval as well. So I have the interval 4 infinity for another interval of decrease. Intervals of concavity of a function's graph. In total sales in thousands of dollars for 2 companies over 4 weeks are shown. We have 2 graphs, Company A and Company B. Company A starts at the point of origin 0, 0, and it has a gradual increase to the coordinate point 4, 10, and as we go to the right, from that coordinate pair, the growth appears to be tapering off as x is greater than 4. For Company B, we are starting at the point of origin with a more dramatic increase to the point 4, 8, with a steep increase going to the right as x is greater than 4. I have 2 tables, Company A and Company B, both of which have 3 columns, both of which are labeled week, sales, and then rate of change. Both of which in the week column, it reads 0, 1, 2, 3, 4. Sales of Company A is 0, 5, 7.1, 8.7, and 10 respectively. Rate of change is blank for now. Company B, again, week is 0, 1, 2, 3, and 4. In the column of sales, we have 0, 0.5, 2, 4.5, and 8. And again, the rate of change column is blank for now. In Company A, if we consider the sales from 0 to 5 in rate of change, I place 5 in that space. From 5 to 7.1, we have a 2.1 delta, which I put in the rate of change column in between the 5 and the 7.1. Then from 7.1 to 8.7, I put 1.6 in the rate of change column. And then from 8.7 to 10, I put 1.3 in its rate of change column. The rate of change of sales over weeks is decreasing. This rate of change column is decreasing in value as we move down the column. Whereas in Company B, if I go from 0 to 0.5, I see the rate of change is 0.5, so that goes in that column. And then from 0.5, and then from 0.5 to 2, we have a rate of change of 1.5. So 1.5 goes in that column. 2 to 4.5, we see 2.5, which goes in that column. And then 4.5 to 8, we see a 3.5 change, which goes into that rate of change column in between the 4.5 and the 8. The rate of change of sales over the weeks is increasing. So surely, because we are looking at these two very different relationships, one of which where the rate of change is decreasing, and the other of which the other in which the rate of change is increasing, surely this should manifest differently on the graphs. So we have a picture of both of those graphs, and what we see is two triangles capturing the average rate of change in between the points 1 and 2 and 3 and 4 on the x-axis. For both graphs, we see these depictions. For company B, we see that the rate of change between those points is larger because this function is growing in its difference as the x value gets larger. When the rate of change is getting smaller, as with company A, we say the function is concave down. When the rate of change is getting larger, as with company B, we see the function is concave up. Concavity. A function is concave up if the rate of change is increasing. A function is concave down if the rate of change is decreasing. A point where a function changes from concave up to concave down, or vice versa, is called an inflection point. Here I have a table which is 2 by 2. The columns are labeled increasing and decreasing, and the rows are labeled concave down and concave up. In the space which is increasing and concave down, I have a picture of a function which is both increasing and concave up. That is meaning that the function is growing, but it is growing at a rate which is tapering off. In the space of concave down and decreasing, I see a function which is decreasing, but its rate of decrease is growing as we go to the right. For concave up and increasing, I have a function which is increasing, and its rate of increase is growing as I go to the right. And if in the space of concave up and decreasing, I have a function which is decreasing, and its change in decrease is tapering off as I go to the right. To the right of this table, I have two depictions, one of which is a frowny face with negative signs in the positioning for eyes, and a happy face with positive, with plus signs in the place of eyes. This is to signify that, or this is to show that a frowny face is an excellent depiction of a function which is concave down, and the negative eyes are meant to show that we would be looking at a concave down function. The positive signs, or up for the eyes, in the case of the smiley face, show the different ways that we can have a function which is concave up. Intervals of concavity from a function's graph. I have a quartic function with both arrows pointing down, with turning points at the coordinate pairs 0, 5, 2, 3, and 4, 5. I start by drawing vertical lines at x equals 1 and x equals 3, because this appears to be where the function changes from frowny face to smiley face to frowny face. And those lines, x equals 1 and x equals 3, partitions those changes from frowny face to smiley face and smiley face to frowny face, respectively. I draw a frowny face around the space to the left of x equals 1 to signify that this function is concave down. I draw a frowny face to the right of x equals 3 to signify that this is also concave down. And then I draw a smiley face through the space 1 to 3 to signify that this is concave up. For concave down, I show an arrow going to the right of the leftmost frowny face, signifying that we are starting our concave down at -infinity to 1. Both of those are in parentheses, so a concave down interval is from -infinity to 1. My other concave down space was to the right of x equals 3. So that's going to be starting at 3 and going to x equals infinity. I'm going to be using parentheses around the interval as well. For concave up, that's going to be from 1 to 3 as depicted by the x boundaries of my smiley face. And after I clear those faces off the graph, this helps me clearly label the points of inflection, which are the points where the lines x equals 1 and x equals 3 intersect with this quartic function. Those coordinate pairs are roughly 1, 3.8, and 3, 3.8. Next, I show an xy grid with a quartic function with both arrows pointing up. The turning points are roughly at the coordinate pair -3.9, -3.9, 0.2, 0.2, and -6.2, -10. I draw vertical lines at x equals -2 and x equals 4 because those are they roughly seem to be the way to partition our smiley faces and frowny faces. An interval of concave down would be from -2 to 4, parentheses around those because that is clearly a frowny face. My concave up intervals would be from -infinity all the way to the left to -2, parentheses around that space, and then from 4 to infinity, parentheses around that space as well. My points of inflection, I draw these kind of poorly, really, at the coordinate pairs -2, -2, and 4, -6, and these are our points of inflection. Thank you for tuning in.